Alright, let's continue the PowerPoint.
Excuse me, teachers, at this time, I need to release the baseball boys down to the gym to get ready to leave to go for their tournament. That's all baseball boys and managers. Thank you.
You will be missed, brother. Yeah. Good luck. So I wanted to go over these octet rule sections. So whenever you're doing the NAS method, you need to count boron as needing 6 full valence electrons, aluminum as being 6, and beryllium as having 4. Hydrogen and helium only need 2. I don't really teach this too much, that's why I kind of skip over it. I don't give these too much examples, but for example, if you want to figure out how many bonds, so how many do you need in total? Well, this is going to have 4. Iodine is going to want to have 8. So we have 1 times 4 plus 2 times 8. We see a total of 12. How many are available? Beryllium only has 2, right? Where's my periodic table? So beryllium only has 2. Iodine has 7. So 14 plus, that's not 12. That's 16 plus 4, which is 20. And 14, that'd be 16. And then the shared is going to be 20 minus 16, which is 4. And thus, using this, we can see that the number of bonds is equal to 4 divided by 2, or 2 bonds. So we're going to just have 2 bonds. Beryllium bonded with I, and like this. And we're going to complete the octet rule on each of them. So I is going to have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. The line gives it another 2. That's 8. Beryllium only needs 4. So 1, 2, 1, 2. And seeing that there's no lone pairs, I would actually prefer you to have written this like this. You should recognize what geometry will this have. Without any lone pairs, this should be linear. So this would be the correct Lewis dot structure. So doing or exception for aluminum. Aluminum only needs 6 valence electrons. Chlorine is a non-exception, so it needs 8. So the total that we're going to have is 1 times 6 plus 3 times 8. That would be 30. The number available. So chlorines all have 7. There's 3 of them. Aluminum has 3. So that'd be 21 plus 3 is 24. And so the amount that's going to be shared is going to be 6. Thus, to figure out the bonds, we simply divide that number. 6 divided by 2, that's 3 bonds. So we're going to have aluminum that's bonded once to chlorine, bonded to another chlorine, bonded to another one, and then we check our octet rule. These are going to need 8 around it. And the aluminum has 6 around it, so it's satisfied. Boron is another exception, it only needs 6. Hydrogen is an exception, it only needs 2. So the total needed is going to be 1 boron, what needs 6, plus 3 hydrogen that needs 2. So that'd be 6 plus 6, which is equal to 12. The amount available currently, well, boron has 3 valence. There's 1 of them. Hydrogen only has 1 valence, and there's 3 of them. So that'd be 3 plus 3, which is 6. And so the shared is going to be 12 minus 6, or 6. And thus we can figure out the total number of bonds is 6 divided by 2, which is 3. And so we see this. Check to add dots until we get the octet rule full. Hydrogen needs 2. It has 2. Boron has 6 around it. So octet rule is done. This is the correct formula. Does that make sense? So you just really need to, if you're doing this method, hydrogen, helium need 2 valence. Beryllium needs 4. And boron and aluminum need 6. Everything else needs 8. And we'll never use helium. Noble gases normally don't react. We have seen some noble gases in the formula, particularly xenon. Why do we see xenon reacting, even though it's a noble gas? Remember, as we go down, the increased size means that the nucleus can barely hold on to those outer electrons because the atom is so big. And so we can get some reactions going on because it can't hold on to the electrons as well. And it's not a metal. It doesn't do metallic bonding. So we looked at molecular shapes. Basically, you make your Lewis dot structure, do all that, and look at your chart. We'll get to that later. I wanted to go over polar versus nonpolar. So, talking about polar molecules. Just because you have polar bonds doesn't mean you are a polar molecule. So, the effect of polar bonds on polarity of the entire molecule also depends on molecular shape. So between carbon and oxygen is polar. So carbon is more positive, oxygen is more negative. Carbon more positive, oxygen more negative. But look at the symmetry and the geometry. They cancel each other out. Now look at water. The oxygen and hydrogen is a polar bond. but look at the direction in which they go. So looking at, for example, oxygen, double bonded with C, we have a positive, and we put a positive, and we usually indicate by an arrow like this. So this indicates that this carbon is positive, and we're going to the negative side. Likewise, we can do the same thing here. So if we look at this, these two cancel each other out. This side is more positive, this side is more negative. But there is no negative, there is no side that's more positive than the other. What's in the middle is doesn't really interact too much. You can't, if you cut this in half this way, we still have positive, or we still have negative, negative, positive, negative, or positive, like that. And if we cut it like this, down this way, we have the positive in the middle and negative like that. It's all symmetric. There's no way I can cut this and have one side that is completely different from the other. But if I look at water, the hydrogen is more positive. So the water side, the oxygen side is more positive, and the oxygen side is more negative. If I cut it like this in half, I have positive and negative here. Makes no difference. It's symmetric on both sides. However, if I cut it along this side, I clearly have a positive side and I have a negative side. So this is polar, has polar bonds. This is a polar bond. And it has polar shape. You can cut it in half and cut it in a certain direction, and you see opposite sides on both of them. So polar molecules have a partial positive and partial negative charge called a dipole. Dipole means that you have two poles, a positive pole and a negative pole. That's what dipole means. Molecules are considered polar only if they have an asymmetrical shape and polar bonds. So asymmetrical shapes include has a lone pair of electrons, has polar bonds, and has different elements around the central atom. So there's a multiple different ways you can get an asymmetrical shape. You can have different atoms, in which case the charges are, that's basically how we get polar bonds. Having different atoms usually indicates that we'll have a polar bond. Not always, like if they're very close together, they might not form, they might form nonpolar if they're very close in electronegativity. Usually if we see lone pairs of electrons, that usually going to indicate that the shape's going to be bent and it's not going to be symmetrical, because the lone pairs are going to want to be on its own side. So this is a symmetrical molecule. The molecule is nonpolar due to the symmetrical shape. It does contain polar bonds. The carbon is more positive than the hydrogen. Oh, I said that wrong. The hydrogen is more positive. The carbon is more negative. However, because there's no way you can cut this to see different symmetries. No matter any way you cut this, it'll be a mirror reflection on the other side. However, look at this one. Do we have symmetry? I replaced one of the hydrogen with a chlorine. Now we no longer have symmetry. There's an unequal pull on the electrons. The chlorine is going to pull more strongly. So the left side of this, left side is going to be more positive. the right side is going to be more negative. So I have hydrogen with carbon, with hydrogen, with hydrogen, with chlorine. So the one with the least electronegativity is going to be positive. So hydrogen is sitting around 2 to 2.2. Carbon is somewhere around 2.5. And chlorine is sitting at over greater than 3. So drawing my partial charge direction, I see that this hydrogen is going to be more positive, so the arrow points this way. Likewise, by symmetry, go down. And carbon has less electronegativity than chlorine, so it's going to be more positive than chlorine. So I basically have this shape looking at my arrows. We can see that these arrows cancel each other out. My overall shape is pointing where I have a positive side on the right or left and a negative side on the right if I cancel out all these arrows and look at the direction. So what this means is that this portion of the molecule is positive, while this portion of the molecule is negative. It has a negative side and a positive side. So the net effect is from positive to negative will be going to the right. Is this polar or nonpolar? Is this a polar molecule or a nonpolar molecule? Yes. Note the PowerPoint is wrong. So hydrogen has 2.2, chlorine has 3.16. That's a difference between, so the difference of En is between 0.5 and 1.7. So that means it's a polar bond. And because of symmetry, or because of asymmetry, I mean, the hydrogen has the least, so it would be positive side. And so we have a positive side and a negative side like that. This means it's polar. We can clearly divide it to a positive and negative side. The PowerPoint calls it nonpolar, but a quick Google search does confirm that it is polar. Eva shows it. There's an arrow you can draw. Is this polar or nonpolar? Carlos, what do you think? Why? It's symmetrical shaped. So here we can see all three of these arrows cancel each other out. Imagine you're playing tug of war on the boron atom. If all three people were of equal strength, the pull of the boron wouldn't be pulled in any direction. The electrons on it can't decide which fluorine atom to go. It's all symmetrical because they're all three the same fluorine. So this is nonpolar. So water is the most classic example of polar. If you've ever taken like a physics class, you can add up vectors. If we look at this, where we have an arrow like that. So basically, you're adding together these two arrows. You can basically break this arrow up into a horizontal arrow and an up arrow, a horizontal arrow and a vertical arrow. These two arrows cancel each other out, and we get a net effect of an arrow just pointing upward. I like thinking in terms of physics and vectors, but that's probably too complicated for this class. You have a net dipole moment pointing upward, meaning the hydrogen side is positive and the oxygen side is negative. Is this polar or nonpolar? Why? Because of what? Is uneven? That's not necessarily the case. We can remember it being uneven, and it still be nonpolar. So this one's a trick question, or let's just say you should look at this carefully. So we have carbon in the middle, and then we have chlorine, and chlorine. Looking at hydrogen and carbon, which one would be more positive, which one would be more negative? Hydrogen would be more positive. So we have the arrow pointing in this direction. Carbon and chlorine, which one's more positive, which one's more negative? Yes. So that means carbon is more positive. And these are all symmetrical. So what I have is down arrow, side arrow. Well, it's still pointing down. So all the arrows are pointing in one direction. That means overall, add these all up, I have a positive side and I have a negative side. Because all the arrows are pointing straight down. This is how you can clearly tell that this is going to be polar. Let's say that I had, for example, I'm just going to make something up. Actually, this is probably more realistic. Let's say I have a fluorine, a chlorine, a chlorine, and a chlorine. Here, the arrows go point up, the arrows go point right, the arrows go point down, the arrows go point left. And this one is very questionable whether or not it's polar or nonpolar. It just depends on whether or not fluorine can pull more strongly than these three chlorines. And fluorine does pull more strongly. It's just because remember fluorine is a 4 and chlorine is a 3.16. This I would think would still be polar, but it'd be ever so slightly polar. Yes.
Where did I get the 4 to 3.16?
The back of this paper.
I don't have that big.
Actually, print a new one out. The bottom is the old one that's been corrected, and it's from the PowerPoint. The top one is what I prefer because it's way more accurate. It might contradict some of the answers in the PowerPoint because the PowerPoint uses the bottom one. There's multiple different scales to use. They're all slightly different. A Pauling scale is the most widely used scale to work on. Again, all of these lines are fuzzy. What we call polar and non-polar, there isn't a hard concrete separation. We just make up one. We just say 0.5 is the cutoff. I accidentally closed the PowerPoint. So, lastly, oh, here it is, showing you that the net dipole moment is down. Lastly, remember that polar and nonpolar molecules are different from polar and nonpolar bonds. Nonpolar molecules have charges that are evenly distributed due to shape. Polar molecules have partial positive and partial negative charges, and their shape allows them to have different sides. So the top one is going to be nonpolar because you can't. There's no way you can slice this and get a positive side and a negative side. Make sense? Alright, last few more examples. We haven't done Lewis dot for ions yet too well. Let me look up some polyatomic ions. What is the Lewis dot structure? Let's start easy. Hydroxide. What is the Lewis dot structure for hydroxide? We know the formula is OH negative. Again, you should have this one memorized. Negative means -1 charge. Means it gains an additional electron. How we do Lewis dot for ions is we're going to initially begin with treating OH as not an ion. So O has 6 valence. Hydrogen has 1. We're going to connect them and try our best to balance everything out. And we're going to, at some point, randomly add this 1 electron. We notice that this oxygen has 7 and needs 1, so I'm just going to add the 1 here. Now its octet is full. Hydrogen is satisfied with 2. This is the correct. This is not the correct. Very important. After you add that 1 dot, we always put Lewis dot for ions in brackets and indicate the charge outside of it. This is the correct way of writing the Lewis dot for an ion. Always put brackets around it and indicate the charge outside of it to indicate that you've added a dot somewhere.
So once you add a dot, you have to flip it around?
Yes. You could immediately begin to, but well, no, because you haven't made it negative yet. You haven't added an electron to. But once you add an electron, you do it. So let's do another one. Sulfate. Try working that one out by yourself. What's the formula for sulfate? Carlos, do you know? We've learned nomenclature for polyatomics. So they usually end. So sulfate is a as an oxyion. Oxyions are usually in the form XO3. Except for sulfur, phosphorus, and arsenic, and phosphorus, sulfur, arsenic, and selenium. All you need to know is phosphorus and sulfur is the exceptions. These are in the form of XO4. So sulfate is SO4. And to figure out the charge, sulfur is... Yes. Sulfur is going to be a +6. Oxygen is going to be -2 times 4. That's a -8, and that's a +6, so we get -2. So this has a 2 negative charge. And again, I haven't really used NAS method in the past. Let me see if NAS method still works with ions. So I have a feeling you're going to have to add those 2 electrons into the formula somehow. Yeah, so if you're doing NAS method, so this is how many you need in total. This is how many you got available. But remember, we have 2 additional available. So, a little hint. So, the total we have, sulfur and oxygen both need 8. So, 1 sulfur plus 4 oxygen. Both of them need 8. That is a total of 40 in total. How many we have available? Well, sulfur has 6 valence. Oxygen has 6 valence. So that's 30. But we also have a random 2 electrons in here. So 32. So thus the amount shared is 8. So the total number of bonds will be equal to 8 divided by 2. Oh no, I did that wrong. You should end up with 6 bonds. So if I remove the 2 here, that's 30, that's 10, and that tells me I have 5 bonds. But I'm going to need to add those 2 electrons. You put the needed up here, I guess. Because we need 2 additional. That's how I think you're going to do it. My bad. So we need this many valence electrons plus 2. That's not a good way of describing it. It works out. You need 6 bonds in total. Why do you add the 2 here to make it work out? Why not add the 2 into the available? Again, I don't use the NAS method. NAS method. Ions? This is what they say to do. The NASL method. I don't call it the L. They say A stands for the number of available electrons. This is equal to the group number they're in. Remember your exceptions. For an ion, count up the valence electrons and add the charge if negative, but subtract the charge if positive. So you're supposed to, for this, N, it's the same thing. We got 40. A, we got 30. And what you're supposed to do is add the charge of -2. And that gives our A now is going to be 28. When we add the charge. We get shared is going to be 12. And thus our L, which is the number of bonds, would be 12 divided by 2, or 6 bonds. I don't like the NAS method because it hides the fact of how the electrons are actually moving and you're not constantly thinking about it. Oh, get it?
I lost myself. one copy.
Alright. So we have sulfur. Sulfur has 6. And then we have 4 oxygens. Which also has 6. So, very simply, we can connect these two right off the bat. And we notice that there are two, these are currently missing 1 electron. These are currently missing 1 electron. I'm just going to randomly, where's my red pen? Just to illustrate that I'm adding it. I'm going to take my 2 additional electrons and just add them there, which makes this 2 negative now. Now all I have to do, what my problem is now, these oxygens I need to bond in here and complete the octet role. So this oxygen is full, it completes the octet role. This oxygen completes the octet role. This sulfur completes the octet role. But this oxygen I haven't bonded in. So what I'm going to do is make sure I got this right. Is move this oxygen, this electron over here. So I'm going to remove that one here, put it here. Remove that one here and put it here. And then I'm going to make sulfur give up or share its 2 electrons. Does that make sense? Does 1, 2, 3, 4, 5, 6, 7, 8. Ooh, what's up with the Lewis dot structure? That doesn't seem right. That gave y'all 2 hard ones. I would have came up with, why does sulfur have 10? I would have came up with this. So they're all satisfied, but let's check. I should have 40 electrons plus 2 additional electrons. So this has 1, 2, 3, 4, 5, 6, 8. What? This has 8. That has 8. That has 8. What is 8 times 4? And then this has 1, 2, 3, 4, 5, 6, 7, 8. It's not the number. But this has 10 electrons around it. That doesn't complete the octet roll. I'll have to look at that. I'll get back to y'all on that. Why is this an exception? Yeah, you're supposed to have 2. I can see how this has 6. I'll have to look it up and figure it out why. It could be wrong. A lot of the times when you Google it, you get the wrong answer. I'm pretty sure that was right. Oh well.